Alright, so today I'm gonna be explaining this important paper with the title Learning Order Autoregressive Models with Application to Molecular Graph Generation. This ICML paper in 2025. We have many different ways for graph generation, but unfortunately these autoregressive models are not scalable. So we have autoregressive model and non-autoregressive model, which are most of them parallelizable. So it means that many of the nodes can be updated at the same time. Unlike autoregressive, that is like ChatGPT, it's very sequential. But non-autoregressive is like BERT. You have many hidden masks, and suddenly all of them will be revealed. And so there are many pros and cons to different graph generation that I will explain them in the playlist for diffusion-based graph generation. Autoregressive models have become the workhorse for sequence generation tasks, since many problems can be modeled as next token prediction. While there appears to be natural ordering for text for many data types such as graphs, canonical ordering is less obvious. For example, in a sentence, you know the natural order, but in a graph, you don't have from left to right or something like that. There is no canonical order. So we introduce a variant of autoregressive models that generate high-dimensional data using probabilistic ordering that is sequentially inferring from data. This model incorporates a trainable probability distribution referred to as an order policy that dynamically decides the autoregressive order in a state-dependent manner. So we introduce a variational lower bound on the log likelihood, which we optimize with stochastic gradient descent. We demonstrate experimentally that our method can learn meaningful autoregressive orderings in image and graph generation. And they work on QM9 and Zinc 250K, these two benchmarks. But the key limitation of traditional autoregressive model is the reliance on predefined canonical ordering or factorizing the probability distribution over data distribution. So, if we have any permutation, there are different ways depending on condition on this permutation. You can have this factorized, this joint distribution that factorizes like this. Because if the length of the sentence is, for example, L, because we have a sequence, each dimension takes value from a set of your vocabulary. But this P of sigma denotes the uniform distribution over L factorial permutations. So we maximize expected log likelihood. So now we describe a convenient way to characterize the sequential generation, which we use for building this method. And so we are learning the policy, how to generate order, how to find the order. What is the order policy? So we have L latent variables. And then you can write the probability distribution like this. But the order policy is, by the definition, is that the order policy is a distribution over Z that follows the factorization. So to train the low R model from a set of training examples, we want to maximize this log likelihood. We only consider one data point for now and drop index n. The joint distribution can then be factorized as this. Now the factors depend on parameter theta that we want to learn, since the exact likelihood is intractable. We will maximize an evidence lower bound on the log likelihood. We use an amortized variational distribution over Z that conditions on the full data vector X. Now we can lower bound the log likelihood as follows. So this part they call it F, and we will use it. We will call it F here. L is a constant, and now we just need to obtain the stochastic estimate of our losses as equation 9. But for this special case where each variational factor are non-learnable and set to uniform distribution, you have this simple negative elbow, which is precisely the stochastic objective used for training AO arms. But the stochastic objective here is more complex, which therefore would have higher variance. But in order to propagate gradient through the sampling step from discrete distribution, we need reinforced gradient estimation. So we use the reinforced leave one out estimator with 2 samples. First, the trick is here. First, we select a single random index, then given this fixed I, we draw 2 samples path, Z1 and Z2, and from them, now we can derive the unbiased gradient like this. So now delta F is this difference. So we compute the RLO unbiased gradient. This is how we train. For sampling, we go through all of these L tokens and sample data, dimension values, and unmask it, and then remove ZI. So the logits are combined in an autoregressive way. Computing and sampling from variational distribution is very fast, since it requires a single evaluation to obtain and store the vector of logits. Since X is discrete, we parameterize the model conditional for L classifiers. So we have this softmax formulation. So they did uniqueness, because when you want to generate a graph, a molecule of, for example, zinc 250, you make sure that it is unique. It is validity. Also NLL, FCD are different measures that you need for graph generation to see if it works well or not. And they compared with graph arm. They compared with graph DF, and they compared with their different versions of low arm. So the uniqueness is 100%. And these are the generated zinc samples. You see, they are very unique and valid. And they also did for QM9 dataset. QM9 dataset, quantum mechanics. Then in appendix, they talk about parameterizing the classifier